Good afternoon, class. Today's lab is going to be on Kepler's laws of planetary motion. The reason why we're doing this lab this way is because I have some obligations this evening that I need to attend to. And I picked this lab because it's going to help you guys on your exam. So let's see. What we're going to talk about today, like I said, is Kepler's 3 laws of planetary motion. This whole lab is going to be based on that, and you guys are going to go through some activities that will help explore some of those laws. And of course, no introductory video for this lab would be without, would be good without having the laws listed. So we know that the first law of planetary motion, of planetary motion, is that planetary orbits are not circular in shape. They are instead elliptical in shape, with the sun located at one of the 2 foci of the elliptical orbit. We also know that the second law is planets sweep out equal areas in equal times. And then the third law is that the period of an orbiting body is proportional to its semi-major axis raised to the 3/2 power. So we can talk about these things a little bit more. And what we need to do first is look at our lab manual. Right now it says that these things aren't published. Once I get the video uploaded onto YouTube and can provide a link here at the bottom, I will publish this stuff, so it will be green and check marked like these things. So you guys will click on the lab manual, open it up, and you'll see that you have a decent document here that will walk you through every activity. I'm also going to walk you through it, but you have not only this, but you'll have my notes that I have here. As you can see, I've marked out things that I thought were important. So what we're going to do next is right here. We're going to identify the parts of the elliptical orbits within the lab manual. So when we go down here, there's an image, figure 1, within the lab manual that talks about the different parts of an elliptical orbit. Obviously, an elliptical orbit means that it's the shape of an ellipse. So some major parts of an ellipse are, the semi-major axis, which is the longest axis of the 2 that it has. And then there's the semi-minor axis, which is the shortest of the 2 axes that it has. And then there's also 2 foci. There's also this special number here called eccentricity, and that's a measure of how elliptical an orbit is, or how egg-shaped it is. And so if you have an elliptical, or if you have an eccentricity of 0, you have a perfect circle. And if you have an eccentricity of 1, you have a very, very elongated ellipse that looks almost like a line with a very, very, very infinitely small semi-minor axis. So other things that I would like to point out, moving on to the second law is that, planets sweep out equal areas in equal times. So if we go to page 3 of our document here, we can see that there's an illustration that actually shows us what that statement means. So what we have here is, maybe this is doesn't specify the specific time, but let's say that this is 2 months, or maybe a month and a half, just a guess. And what if we drew a line from the sun to the planet and then kept that line there throughout the whole month and a half, it would sweep out this area that we see here. The planet itself would follow along this path labeled as arc 1, and the line that would be attached to it from the sun would sweep out this area 1. So if we go and we wait some time till the same planet is at the other end of its orbit, we can then, draw another line from the sun to the planet, allow the planet to move for a month and a half, along this distance arc2, and the line that's attached will sweep out this area 2. And these two areas will be equal to each other. So you might ask yourself, okay, that's all confusing. Why does this even matter? Well, this is a huge thing. And the reason why it's huge is because what that means is that planets that are orbiting around a main body, or anything orbiting around a main body, orbits at different speeds throughout its path along its revolution around that body. So here, around arc 1, the planet is moving much faster than it was over here by arc 2. Due to the distance that it is, or that the planet is from the sun, while it sweeps out this second area, it happens to sweep out, well, happens is a very bad word, but we show that these areas are equal. Later on, when we get a little deeper into this lab, we will see Newton's modifications actually help explain why a lot. So if we move along, the third law for Kepler's planetary motion is that the period of an orbiting body is proportional to its semi-major axis raised to the 3/2 power. So there's no fancy image to go along with this one. This is the mathematical statement that kind of embodies the other two statements. So we talked about this one in class a little bit. Yes, for both labs, we talked about this specific formula when we were talking about the homework problem back in chapter 2, I believe it was. So the next thing that we want to talk about is actually the modification that Newton made to Kepler's 3 laws. But the first thing that we want to, kind of remind ourselves of are Newton's 3 laws of motion that he himself established before he modified Kepler's. The first law that Newton, or the first statement of Newton's law, or the statement of Newton's first law, there we go, that's the proper wording. An object at rest will remain at rest unless acted upon by an outside force. Also, if an object is in motion, some constant velocity, it will stay at that constant velocity unless it's acted upon by some outside force. And the second law for motion by Newton is that when a force acts on a body of a mass m, it produces an acceleration. Those of you that are in your first year physics class are learning this or have learned this. And Newton's third law is that when one body exerts a force on a second body, the second body exerts a force equal in magnitude, but opposite in direction on the first body. So this is kind of important, and there's a reason why I stated these things, because we want to keep these fresh in our head, because when we go to the modifications, it'll help us to understand more why these things these modifications are much better. So before we get too far into these modifications, I want to talk about some repercussions of Newton's laws. Some things that I think are pretty fun. And orbital velocity and escape velocity. Those of you that might have played Kerbal Space Program might know that it's pretty hard to get off the planet, and it creates a dazzling spectacle of fireworks when you don't. So part of what you need to know if you're going to get off the planet is how much velocity you need to apply to yourself away from the planet to get off the surface. So what we look at is we look at how much energy is coming from, like gravitational energy is coming from the planet or the sun, whatever object it is that might be orbiting the heavier object. And you guys probably talked about this in class, but when we talk about the gravitational energy between a body that's orbiting a bigger body, we can then think about the kinetic energy of the moving body, and we can start to play around, and we can use that relation to find a velocity And I've outlined it here in my notes as a side note. Like I said, we have this is for orbital velocity if you're interested in this, but I mainly want to focus on the kinetic or the escape velocity. And as you see here, it's just setting the energy of the different bodies equal to each other and finding that there's a specific velocity at which a planet can go before it's going too fast for it to stay in its orbit. And it's pretty fun because then you can talk about it colliding, and then you can think about comets and asteroids and things like that, things that don't stay in our solar system when they come by. I think we might have had one of those not too long ago. There's a lot of speculation that it might have been a UFO and all that good jazz because it accelerated as it left the solar system, which was interesting. So with that little sidebar, I want to move on to Newton's modifications. And what I really want to do is just briefly mention how Newton modified these three laws. And for Kepler's first law, Newton's modification took form, that the orbiting bodies orbit the center of mass of the system. And so if we take a look here at this figure, we can see that there's a scale and that there's this, fulcrum in the middle. And we have two equal weight objects. And it's balancing the scale. So now if we were to imagine removing this 10 kilogram mass and replacing it with a 20 kilogram mass, we would see that this part would come down and this part would raise. Well, we can take this fulcrum and we can move it until the 20 kilogram and the 10 kilogram balance each other, and it produces this graph or this image. So we can extend that idea by swapping out the 20 kilogram mass and putting in a 100 kilogram mass or heavier. And what's going to happen is this fulcrum is just going to keep getting closer and closer and closer to the heavier object. So what this fulcrum represents is the point of center of mass between the two systems. And Newton's modification explained that the ellipses that we were seeing were due to the fact that one of the foci of the orbits for the ellipse was the center of mass. Kepler did not see it that way. He just saw the foci as being the sun. If you think about, too, what we talked about in class a couple times, this also will extend very, very well out to different things like the sun going around the galaxy or a miniature galaxy going around our galaxy, and two galaxies that are stuck in a dance until they're finished colliding. These things all obey Newton's modifications to Kepler's laws of motion. So if you think about the sun going around the center of our galaxy, the center of mass is pretty much underneath the black hole, and our sun would be some little dot over here. So if we move along to Kepler's second law, Newton's modification here came in the form of understanding that the velocity of both bodies in orbit produced, I'm sorry. Okay, here we go. So I wanted to show you guys this equation. This ended up being Newton's modification to Kepler's second law. Kepler's second law was that equal areas are swept out in equal times. And remember that I said that the consequence of that meant that the velocity of the body orbiting changed throughout the entire orbit. And so you can show that here using the vis-viva equation. And A is the semi-major axis, and R is the distance from the center of the body being orbited, or in this case, the sun. All right, so moving along to Kepler's third law and Newton's modification to it, being that he found and invented calculus and discovered universal gravitation, he saw that you could rewrite Kepler's third law in terms of units humans were used to on Earth, because Kepler had it to where it was just based on you could only write it in AU and it could only be in years. But when when Newton came along, he said, "Oh no, we can do that for any type of time. We could measure it within seconds, and seconds would be fine as well." And that's really his part. As you can see here, before it was just p squared equals a cubed. Well, now we have this constant out front, and I'm sure you guys have seen that in class. So real quick, what I want to talk about is what we are doing in this lab. So in my notes, I put in the links throughout everything, throughout all the text. At different spots, you can find the different things that you need. And I tried to make it as accessible and easy for you guys as possible. So up at the top here is the lab manual, but you also have it on Canvas. There's also a link that's inside that lab manual. In fact, let me just click on this and go back here. This link no longer works. So if I click on it, it's going to tell me that Flash is no longer supported. That's cool. That's fine. People have fixed that. And if you click on this link, which I've also provided on Canvas, it will bring up the simulation. If you've taken this class 153 or 154 before, you might have maybe had this lab. And if you have, this is the only part that looks different than the previous one. If you have no idea what I'm talking about, great. Forget everything that I just said in the last few seconds. So what we're doing in the lab is we're going to play around with orbits. And as you can see here, we have this big mass and we have this little mass, and we're going to try to make this little mass orbit the bigger one. And the way that we're going to do that is we're going to input these different parameters or different things for these parameters here, and we're going to hit the play button. And so just to show, I'm going to put this on accurate, and I'm going to hit play. And as you can see, this thing makes a pretty elliptic orbit. It has a pretty, it's got a decent size eccentricity. And the reason why I say that, the reason why I say that is because the sun, or the bigger body itself, is also moving in a circle. It's another indicator that there's some eccentricity to the orbit, because if it was a perfect circle, the bigger body would not move at all. It would just stay fixed in the center and the planet would orbit it. So that's a demo as to what it looks like. More as to how it works. Like I said, these are the different parameters. You have the different, you can set the mass, you can set the x position of the central body or the orbiting body being body 2. If you understood how to use this completely, you could do whatever you wanted, and it wouldn't matter what body 1 or body 2 is. But we're following the instructions in the lab manual, and the instructions in the lab manual, go ahead and pull that up, tell us that for this specific activity, being the first activity, we want to set these certain parameters to be certain things. And so it says to set the x position and y velocity of the planet of the, sorry, I should start with the first set of instructions. So what we want to do is we want to measure the period of this orbiting body. And what we want to do is we want to allow it to orbit 5 times before we stop it. And then whatever time that it gives us here, we want to divide that by the number of laps. 5 is a pretty good number for the later runs that you'll do. 5 is a pretty hard number for the first few runs because it's pretty fast. I prefer 10. If you're comfortable with 5, go for it. If you're comfortable with 1, go for it. So let's see. Now, what we're going to need to do is, as you can see, there are certain parameters that stay constant, and that would be the mass of the sun and mass of the planet, or mass of body 1 and mass of body 2. The y position of the planet always remains the same, but the x position changes. The x velocity of the planet remains the same, but the y velocity changes. And there's a reason why. It's going to help us to find these two columns of information. So what we want to do to set up the simulation is we want to set body 1 equal to 500. And what I'm going to do is I'm going to walk through the first one for you guys. And by setting that one to 500, we're going to set body 2 to 10, which it's already 10. And then we're going to set the x position of the star to be 0, which it's already 0. And then we're going to set the y position to be 0, which it's already 0. We're going to set the x velocity to be 0 and the y velocity to be 1 for the star, which is here, it's already there. And then for the x position and y position of the planet, we're going to set that to be 0. Why does that say 0, 0 though? Oh, set the y position and x velocity to be 0, which it already is. So now we want to come down here to our table, and this green column is going to be the x position of our planet. Since it's 10, we want to set this to 50, and we want to set the y velocity to 320. All right, so now I'm going to keep it on accurate because it's going to allow it to run slower, but I can also set this to be fast, and it will allow the simulation to run faster. Before I do this, there's this view options box in the top right corner. I want to go ahead and click everything on because I'm going to need all this stuff. We're going to click and drag the center of our tape measure to the side for now. And then we're going to hit play, and we're going to count how many times this thing goes around. We're going to count 5 times how much this thing goes around and then see the time. So here we go. 1, 2, 3, 4, 5. See, I was a little off. So this says it's about 5.1 seconds. I would have to argue that that's pretty bad. That might even be 4.5-ish. So what I'm going to do is can't record my data here, so I have to go back to my Canvas page, and there's this other link that comes with the lab, and it's a spreadsheet. And what we're going to do is we're going to open this spreadsheet in a new window, and it's going to be some template. And you're going to want to click Use Template. And then if you want to, you can click here, and you can click the green share box, and then you can share this with me. It's not 100% necessary, but the lab report you do need to share with me. But this is kind of like your calculator. So semi-major axis and period, these are the two things I need. This is the first run that I did, so this is where I'm going to input my data. How do I get my semi-major axis? Well, I get that by taking my tape measure that I have and setting it in the center of the sun in our case, and setting this to be what we think is the longest point. And I think that's the longest point. In fact, I might be able to fix this. We want this to be as dead center as possible. And so I'm measuring the semi-major axis to be 46. Okay, so I'm going to put that into my data. And then the period, Well, we counted 5 laps and we got a time of 5.1. So what I would do is I would do equals 5.1 divided by 5. That's going to say that my period was 1.02 seconds. Okay, so then you go through and you do the same thing for the rest of these, and you'll fill this out, and you'll see that there's this graph that populates here. This graph's going to provide you with an equation. It's going to give you some information. It's you should definitely try to rationalize with yourself if what you're seeing is proper. And what I mean by that is, does this equation look like something you've seen? Which it should. So once you go through the first activity, we creep along to the second activity where we're applying what we just did, but to things within the solar system. And what we're going to do is we're going to take these different objects and we're going to pay attention to our units in the columns, and we're going to convert and do math, follow the questions, and it's going to guide you through, finding these quantities. It says here in the instructions that you can use the spreadsheet here. You are definitely welcome to. I started it when I created the answer key. I started over here and I just put an AU, and then I went over here and I saw 0.72, 1.0, 2.72, all that good stuff, or 2.77, sorry. 30.1. And then I just let the spreadsheet do all the work. And so I'll do the first one for you. So question number 4, it asks you to convert. And it tells you that 1 AU is equal to 1.496 times 10 to the 11 meters. Well, what joy, because that's what our column is the units of our column is. And so what we're going to do is, those of you that might be familiar with spreadsheet math, you know what I'm doing. If not, whenever you're trying to get a spreadsheet to act like a calculator, you want to press the equal sign inside the cell, and it will begin to think like it's a calculator. And so we can now use the notation and nomenclature of spreadsheets to do our math. A lot of fancy words to describe something simple. So watch. I'm going to take the information that is in the cell 0, I mean not 0, but 05, and notice that it lights up. I don't know why I pointed, but notice that it lights up, indicating that we're using that data point. And then we're going to multiply it by 1.496 times 10 to the 11. Okay, so notice that I didn't write the times 10. That's captured in this E. So what this says is 1.496 times 10 to the 11th power. So when I hit enter, it does all the math for me. And the beautiful thing is it suggests to autofill the rest of the column for me. So if I click this, bam, it does the whole thing for me. I only had to do one math problem and it did 4. So pretty good trade-off. So you can continue to fill out these columns until you arrive at your period in years. This is the Earth. You know you did this right if your answer at the very end is close to 1. Because we know that the period of Earth is not just 1 year, it's 1 year and a little bit more, right? Because we have a leap year every 4 years. So keep that in mind. That's your sanity check when you're doing this. And I'm sure you'll watch this video again. All right, so the next thing that we want to do is for activity 3, we're going to focus on some of the modifications that Newton made to these laws that Kepler came up with. And mainly what we're going to be focusing on is this part of the equation and this part of the equation. You can look here at this image to understand this middle step. But when we go to the third activity, as you can see here, we're given this m1 over m2, and it wants us to calculate the ratio. And then we calculate a1 over a2, and we compare our answers. Okay, so how do we do that? Well, we go back to the simulation, and we set our parameters to what it discusses. I'm surprised that didn't. There we go. So here it tells me set the following initial conditions for our simulation. I didn't say this yet, but to rewind everything, you want to click this button. It'll reset the positions of your bodies. If you click, it's not on this one, never mind. So body one, the masses are going to change, so we're not concerned about that. But the x position of body one is going to be -80. The y position is 0. The x velocity is 0, and the y velocity is going to be -125. For body two, we don't care about the mass right now because we're just setting the initial conditions. We're going to set body two at a positive x position of 80, a y position of 0, an x velocity of 0, and a y velocity of 125. So we'll have two bodies that are constantly going in opposite velocities, and hopefully they orbit each other. So, real quick, you cannot start your simulation here and say, okay, this is my semi-major axis. You have to wait until they've orbited and then identify the semi-major axis. Then use the tape measure to measure that distance. Because if you do it this way, all you're doing is putting 160 units between the two of them. And we can verify that here. This is about 160. So let's take a look. It says here for simulation 1 to set m1 equal to m2, which is 300. So I'm going to set m1 to 300, and then I'm going to set m2 to 300. All right, so now we have two bodies that are equal in mass. They are symmetrically distant apart, and they are moving in anti-symmetric velocities. So I'm going to make it go slow, and I'm going to click this. This little zoom out box will allow me to zoom out. In fact, let me just restart that. All right, so we have now established an orbit, one full orbit. And what we can do is we can measure, we do need to be consistent here. We need to make sure that we're consistent so that way we don't get confused. I'm going to say that, well, as we can see here, body one is yellow or orange, whatever color this is, and this is like a pinkish red for body two. So what we're measuring right now is body one, and this is A1 that we're measuring. So I measure A1 to be 479, 478 probably. No, 479. Okay. And so then for orbit 2, I also measure 479. So think about this as you're going through here. I don't want to do your work for you, but I did just walk through this first one pretty much. You're going to do that a few times and come up with predicted values for your different semi-major axes. So before I finish this video, I just want to make sure Yes. I want to cover these last few things. For the first activity that goes along with this, I found it most useful to turn everything on in the menu in the top right-hand corner. You can read through the rest of these bullet points. Also here, be very wary of the units and the columns when you're doing the second activity, okay? You're going to have these notes too, so hopefully you read them as you're doing this. The third activity, you want to make sure that you read the lab manual as it describes the equations and how to calculate the desired quantities. So these things will help you. As you can see here, I've linked the same simulation later on in the notes, so that way it's there for you. You don't have to go back to anything. So in terms of instructions, that's pretty much it. For bureaucracy purposes, we're going to we want to make sure that you share your lab report with me, which your lab report can be found here on Canvas. Once I publish everything, you'll click on the lab report, you'll click open in a new window, you'll click use template, read these first 4 instructions here, change the name of all this jazz. And then you click share and share this with me. Make sure that anyone with the link has the ability to be at least a commenter. I have to at least be a commenter or an editor. I believe that sums up that one. Please be sure to work on some of this by Saturday if you can, because Sunday I will go through, if I'm not driving, I will go through and check y'all's work and make sure that you're on the right track, provide you some feedback. The lab report, I'm actually probably going to move this. Will be due Friday, October 14th by 11:59 p.m. I know that you guys have your test on Monday, so I want to give you an extra day to work on it. So please be sure to read the lab manual and be sure to copy your work from your Google Sheet to your tables in your lab report. All right, I want to say that again. Be sure to copy your work from your Google Sheet to your tables in the lab report. I don't want you to be submitting an Excel sheet and a document. So I only want just the document. I want to ask you guys if there are any questions, but this is a video. So what you can do to ask me questions is you can hop on Discord and you can ask me all the questions that you'd like, or you can shoot me an email. And we'll see what we can do. I hope you guys have a great week, and I will see you guys next week.